So I'm here to talk about optimizations, and that's because it's fun, and because this picture, I think, is great. But wait, the first question you should ask yourselves is your program actually slow? By which we mean, do you think it could go fast? And there's a meme hidden in here somewhere. And lastly, and the most important question is it worth optimizing and spending that time in doing that? So enter a silly example. We've got a function that simply copies a list of strings. So it creates a new list of strings and then just appends the elements from the old one into the new one. That's pretty simple. Now we create a benchmark that takes a static list of strings and then reports the allocations for copying said list of strings n times, and also how long each of those copies takes. So we can run that benchmark with GoTest, and we can say that it takes about 5,000 nanoseconds per run, about 10 allocations, and create some garbage, as we would expect. We can get a CPU profile out of this benchmark, and if we use pprof to see what's happening in this function, you can see that most of the time, of the CPU time, is spent in the append line. So what we can do is pre-allocate that slice, and then just assign each of the elements. And what happens with that, as you might expect, is that we only allocate once, and it's much, much faster. It's less convenient, but it's faster. So we're done, right? Thanks for listening. But this is a silly example, after all. Enter a JSON benchmark. Now, if you have ever done JSON in Go, you might realize that it's a bit of a controversial topic. It's a good package. It's not great. I'm a maintainer, and maybe I shouldn't be saying this, but there's a benchmark called Code's Decoder, which decodes a fairly large JSON file into a struct. And if you run that benchmark, you can see that it runs at about 200 megabytes per second, and it ran 100 times this benchmark. So you can see that it's not a very fast benchmark. You can see that that's a lot of nanosecond zeros. So this benchmark is slow, but the bigger problem is that it's not going to stay still. If you run it a bunch of times, you can see that the relative speed of this benchmark jumps up and down by as much as 4%. And this might not make a lot of sense if you don't think about it that much. And this is a problem because the recent JSON decoder speedups have been as small as 1.3%. So how can you possibly measure progress with this much noise? And the answer is math, or rather statistics. Now, please take what I say with a grain of salt. I'm going to remain practical because I only took a couple of classes in math in university. That was a long time ago, and I was asleep for most of them. So I'm not going to talk about theory. I'm mostly just going to talk about how you can use statistics. The idea is that you want to get multiple samples, and with that you can measure variance. So instead of using benchcomp, which just compares two numbers straight like that, we're going to use a tool called benchstat, which I believe was written by Russ Cox initially. So what we do is use tests count flag, and that gives us a number of measurements. So in this case, if we get 8 measurements for this benchmark, we can tell benchstat, OK, give me stats about these numbers. And you can see it tells you roughly it takes about 10 milliseconds per run, up plus minus 3%. So that's your variance. But we still need less noise. And what we should think about is our machine actually idle? Now, you should meet my work friends. I tend to have a couple of browsers open, a couple of Slack windows open because it's 2019, a couple of editors, my music, maybe email, and so on. So my CPU usage when idle, quote unquote, sits at somewhere between 0 and 15%. But this benchmark demands all of my CPU. So if Slack suddenly decides to do something, then my benchmark is going to get slower, right? And here's a fun fact about Slack. And it's just an example. I'm not trying to hate on it. But at least until recently, the way it rendered GIFs was with the CPU. So each of these dancing badgers, which we use a lot in the tools channel, it consumed about 2% of my CPU. So if somebody, say Paul Jolly, would send me 50 badgers at once, that's all of my CPU being burned. And I wouldn't even notice otherwise. So you should close resource-hungry apps. And you should get a CPU usage that's a few % at most. And that's OK-ish, at least for a laptop. So if we rerun the same benchmark 8 times, you can see that the variance is now down to about 1%. And We can work with 1%, but we have still another problem, at least with laptops, and it's that the laptop burns. It gets really hot. So at least, for example, with my laptop, after about 10 seconds or so of running at full speed, it's gonna get much slower. Now, why is that? The reason is that laptops throttle, at least modern ones, and I've got some evidence for that. So this is my laptop with my blue Gopher on top of it, and you can see that the ear vents are tiny. They're even smaller than the Gopher itself. And this laptop has 4 cores that can go pretty fast, and the ear vents measure less than 2 Gopher feet, which is a real unit of measure. So in practice, whenever I try to benchmark or measure anything with my laptop with no extra tooling, this is pretty much what happens. My lab just sets on fire. So the idea here is that we cannot use turbo speeds, the maximum CPU speed, because the laptop cannot maintain that speed for a long period of time. So there's a tool for that. And this one was written by Austin Clemens, who's also in the Go team. It's called PerfLock. And it does what you might think from the name, which is it logs a certain performance in your CPU. So you run the daemon. That should be with a sudo, because it needs root. And then you can tell it, please run this command at a certain maximum CPU speed. So in this case, I found that 70% is a speed that's fast enough to be realistic, but slow enough that my laptop doesn't heat up and then throttle. It still heats up, but at least the fan can keep up with that. So after 20 or so runs, you can see that it's consistently slower, but it's consistent. That's what matters. There's a small caveat, and that's that this only works for Linux. It should be portable to Mac and Windows. If any of you want to spend time with that, please go talk to Austin. You can probably flag him down somewhere in the conference. So if we gather 8 measurements before and after of this benchmark without actually changing anything, we should see that even though the averages might change, benchstat is smart enough to tell us the variance is too high, so probably nothing actually happened here. There's no significant change, and that's the delta with the symbol that you see there. Now, you might have some questions, such as what count should I use, 8, 10, 20, or what's a p-value? Now, I'm not going to delve into the details here, but here's how I think about it pragmatically, which is that if you've got high variance, you want a higher count to get good results, or at least meaningful results. And here's a visual aid. Suppose that each of these little fat gophers is a data point. So if it's higher up, it's a slower benchmark run, and if it's lower, it's a faster benchmark run. So you run it 3 times before and 3 times after, and you're wondering, did I improve anything here? If you've only got 3 points, maybe one of them you just got unlucky, and Slack was renting some GIF or something like that. So if a single one of those points got a tiny bit lower on the left, maybe the result would be completely different. What if you have 10? If you have 10, as a human, you can sort of realize that there's a cluster of gophers further up on the left, and then a cluster of gophers further down on the right. It's unlikely that many of them, in that many cases, you got unlucky at the same time. So this is roughly what a higher p-value would mean. But here's a gotcha. You shouldn't be searching for p-values. And this is called the multiple testing problem. That's just a technical term for it. But the gist of it is, when we spoke about benchstat, which compares single runs, if you keep running the benchmark over and over again without actually changing anything, the numbers are going to be jumping up and down, right? If you do that with benchstat, benchstat is going to be smart enough to tell you that most of the time nothing is actually changing. But if you keep hammering it, because it's statistics, about 5% of the time, you can actually get a false positive result, if that makes sense. So in this case, I ran it 5 times, and on the 5th, it told me maybe something improved, but I hadn't actually touched any of the code. So if the data looks bad, don't try to get new data until you're happy with it, because then you're going to run into this problem. And I have done that many times before, and Austin wasn't happy with it. So here's an XKCD, because obviously there's one, that sort of explains this problem. A company gets its scientists to test the relation between different colors of jelly beans and acne. And they run the test with so many combinations that statistically one of them shows a true result. But it's not a true result, and it's published, and it says 95% confidence. But the joke here is that they run it so many times that that's how statistics work. It's a false positive. Now, here's a small side note that I think I should mention, and that's bottlenecks. I've been talking a lot about CPU loads. So tools like pprof and PerfLock, they work purely on the CPU. But statistics, and in this case benchstat, they work on all benchmarks, even if your benchmark is benchmarking network activity or disk activity or syscalls or anything else. So to recap, you should use benchstat to compare statistics and get information from them, and PerfLock if your laptop is too noisy or heats up too much. So now we get to the fun part, and please don't worry if you don't follow every single slide. I will publish the slides later so you can try these commands later. The first trick that I think is quite useful is you can ask Go build with the M flag twice. You can ask it which functions could have been inlined, which function calls could have been inlined but weren't, and why. So in this case, in the I/O package, a call to copy buffer wasn't inlined because the function was too complex by just a little bit. So maybe if that function is really slow and you want it to be faster, maybe you can tweak the code a little bit to get the compiler to do what you want. I'm not saying you should do that, but you can do that, and it's interesting. Another thing that the M flag can tell you is when expressions escape to the heap, which is when they cause allocations. Now, allocations are not a bad thing per se, but if you've got a very hot function that generates garbage and you're trying to figure out where is this garbage being generated and why, maybe this can help you a little bit. There's also BCE, which stands for bounce check elimination. Now, a bounce check in Go is, for example, when you index into a slice, if your index is out of bounds, the runtime is going to panic, right? Because you're not allowed to do that. So the compiler inserts a check whenever you do that kind of thing. So this is what, for example, found a slice in bounds. That's that kind of check being added at this position in your code. You can also ask it information from the proof pass, and the proof pass tries to prove things, such as maybe I can prove that this slice bounds check isn't actually necessary because I know statically that it's always going to be within bounds. So in this case, it can tell you the cases where it is removing those bounds checks. And if you increment this debug value, it can tell you more information. It might not be useful to you, but maybe you find it interesting. And there's a gotcha that I also want to cover, and that's when code suddenly gets slower or faster, and you don't know why. Here's an example, and I hope Roscox is not in the audience. It's from 2011 in the JSON package. You might start seeing a trend here. And it says, I cannot explain why benchmark skip value gets faster. Maybe it is one of those code alignment things. Now, he changed some part of the JSON code base, and then this benchmark, which is entirely separate, suddenly got faster. Why is that? And the short answer is that modern computers are complex, and in this case, code alignment could affect the CPU cache. Now, I don't know anything about hardware, so I'm going to leave it at that. But the answer, sort of the useful bit of information here is that sometimes you just cannot tell why a computer is doing what it is doing. But the compiler is getting better. For example, it used to be that the best way to empty a map was to just completely create a new one. That was fine and fast, but it also threw away all of that allocated memory and allocated an entirely new map, so it generated extra garbage. And since Go 1.11, if you actually range over the map and delete all the keys, that's compiled into an efficient function call, which actually efficiently clears all the elements without allocating a new map. It also used to be that without using any standard library package, the only way to efficiently count the number of runes in a string was to iterate over said string. But since Go 1.11, if you take the length of the rune slice of the string, it is not going to copy the string, and it is simply going to give you the number of runes. So please give the compiler a chance. And if you think it could do better, please file bugs so that it can actually get better. There's a label on the GitHub issue tracker you can use for this. It's called performance. There's quite a lot of stuff in it, but it's good to be able to search for it. And if you want to go deeper, and this is the last trick I'm going to cover, there's an environment variable called GoSSA func. And if you give it a pattern and then build a package, it's going to give you information about how the compiler built that function. So for example, you've got a hello world function that just prints something with println, and then you ask it, go SSA func equals hello world go build, and it generates an SSA.html file. Now, if you open that, there's going to be a lot of information, so I'm just going to skim through a few bits. The first bit that it's going to give you is what the compiler quote-unquote starts with when compiling this function in SSA. And at the far end of it, it's going to give you the assembly that it generates for that function. But the interesting bit is that between those two steps, it's going to show you all the optimization passes and all the changes to the SSA that the compiler did. So for example, if you expected the compiler to optimize a piece of code, but it didn't, maybe this generated website can perhaps point you at where it went wrong. And if you want to learn more about the compiler, there's a couple of Readme files that you can read. They don't go into details, but they give a good introduction, and then ideally they should point to other places where you can learn more about specific things. Cool, so now we get to the demo. I'm going to stop talking because I know that's not particularly interesting. And this is a demo including benchmarking and pprof. So it is likely to go wrong, so please don't be too harsh. Cool, so we are in a clone. We are in a clone of Go 1.12.7, and that's built from source. Now, I want to improve the performance of the JSON decoder, right? So what I can do is go to the source of the JSON package, and there's a benchmark that I like using quite a lot. It's called Code Decoder. It's the one I showed earlier. And what this does is it decodes a very large JSON into this data structure. It's just a struct that has a tree-like structure inside of it, and then each tree element is a struct itself. So it's basically decoding structs and floats and ints. That's pretty much it. So what we can do is first, so the first thing we can do is sudo PerfLock daemon to actually start PerfLock so that we can use it. And then we're going to get the first benchmark numbers from this benchmark. So we can do go test. We don't want to run any tests, so just the benchmarks. So bench equals code, decoder. We're not interested in vet, which is a default now. Yay. What else? Oh, PerfLock. Now, we set 70%. If I use anything more like that than that, my stand might set on fire. And finally, we just want to tee that. Cool. Oh, I forgot one flag. So we want to get 6 measurements, which I think is a decent number to start with. Cool. So once that finishes, we can run benchstat on the resulting file. And we can see it runs at about in 12.7 seconds, plus minus 1%. And so we want to improve the performance of this benchmark, right? So one thing we could do is use a pprof profile to try to see where we could improve. So one way to do that is to use the benchmark itself to get a profile. So we can do go test, kind of the same thing we did. We don't need PerfLock for this. Well, sure, why not? We run the benchmark. We only want to run it once, and we want to run it for a little bit longer. The default is 1 second, but we want to run it for, say, 10 seconds. And then we want CPU profile, CPU.out. This is going to take 10 seconds. So once that finishes, we're going to get a CPU profile, and that's going to tell us where the benchmark spent its CPU time. Cool. So if we do that, oh, it's running somewhere else. Ah. Great. So the first view it gives us is a graph that shows you, so it begins, whoa, this is very sensitive. Whoa. Okay, I'm just not going to zoom anymore. So you can see that most of the time is spent in these big boxes, which are functions. So one piece of information that I find really useful is top. That gives you where the most of the CPU time was spent per function. So you can see, for example, the flat % of time that was spent in each function, such as scan while. Now, you want to look at these functions that take a lot of CPU time and try to see how you could optimize at least, for example, one of them. So what we can do is go into source, and this gives us the source for each of these top CPU users. Now, usually what I would do, oh, I selected one. Why is it not showing everything? Oh, there we go. So I could search one by one and see which line I could optimize. For example, this line takes 2.74 seconds out of the 10 seconds, which is a long time. But I already tried to optimize that, and it doesn't work, so we're just going to skip past that. Now, I know ahead of time that there's something we could do here, which is there. So you can see here that we spend a total, so the first number is how much CPU time this function uses, and the number on the right is how much time the function and all its subcalls use. So we can see that this function in total uses 1.6 seconds, and this another second. That seems like a lot, because the others around them don't use much time. And look, it's the function that finds what field to decode into in a struct. And that's something that you do a lot. When you decode a struct, every time you see a value, you have to map it to which struct field you need to decode into, right? So I think this isn't very performant. I think we could do better. So let's go and do better. So let's kill that. Cool. So it's this piece of code. Can everybody read that? If anybody cannot read that, please raise your hand. OK, great. So what this piece of code does is it first tries to find an exact match, and then it tries to find a case-insensitive match. But if you think about it, the happy path is that there's one exact match, and that's it. But what you're doing here is linearly searching one by one, but you're also doing the case-insensitive search at the same time, which is very expensive. So what we could do is use a map, because we can, for example, use a map from string, which is the key, to int, which is the index of the field, of the struct field. So where's this field's data structure defined? It's a slice of field, and each of these fields holds information about decoding into that field. So you can see here type field, name bytes. Equal fold is what compares that in a case-insensitive way to some byte slice. So what we're interested in is what we want to do is we want to add a map to this. So we're going to add a struct type. Oops. And we're going to add two fields, a list of field, and then let's call it index. Map from string to int. So then this should return struct fields. This just finds the fields and creates a slice. Not particularly interesting. And then towards the end, it just returns the fields, right? So in here, instead, we want to return, we want to create this map. And then for each of these fields, we want to say, to index that field, we're going to do index f.name equals I. And then here we're going to return struct fields. And we have the list of fields and then the index. And I'm not using keys. Please don't shout. I think that's it. Oh. The JSON decoder also caches these data structures, so we also have to update this. So bear with me for a minute. Type fields and then returns. Great. And now, whoops. Oh, there we go. So we've got the fields slice. OK. So that's going to be a struct fields now. And instead of doing this linear search, what we're going to do is first, if f, OK, fields.index. So key is a byte slice, but we can do a string key. And recent compiler versions are not going to copy this key byte slice because we're just using it to index. So it's going to index directly with the byte slice without copying or allocating. So if we found it, then cool. And then if, then else. If we don't find it with the map, with this index of ours, then we do the expensive linear search. But because we already did the case-sensitive search with a map, we can simply remove all of this. And we know that f here is going to be nil. It's not going to be, yeah, it's going to be nil. Cool. Great. I believe that's it. Now, I'm going to try it. It's probably not going to work. Ah, there we go. It doesn't work. Go imports. Can I just have to decode 698? Oh, it's an index, not a field. Duh. So f equals fields.list, and then the index. Ah, thank you. This is very realistic because I do make lots of mistakes in real life. List. Sorry, pointer. You can tell this is real because I'm making lots of mistakes. We only have one mistake left. 670. New struct encoder fields, get stick fields. Why does this need a field list? Maybe? I don't remember. OK. This broke something. We're going to ignore that for now, please. Thank you. We're going to ignore the tests for now because I don't have time to fix that. And we're just going to focus on the benchmark. Great. So thanks for helping. So what we want to do now is grab new benchmark numbers and then compare them with the old ones. So we want to do the same thing, but then t into new. And we wait. Now we check old, new. Great, and it got about 5% faster. Now, this is good. It's a speedup that went into 1.13, so it's already in master. This is why I'm doing it on top of 1.12. The fix in master does not introduce a bug, I can tell you that much. So great, we're done. But we've got time, so I'm going to do another demo. So this demo is a change that's not in master yet, and a change that I haven't tried yet. So you can find out with me whether it works or not. And if it doesn't work, that's going to be maybe a low end to the talk, but we'll see how that works. Great. So let's leave this 1.12 version, and enter master. So, 1 second. Whoop. Great. So if we do go version, so this is a version from a couple of days ago. Same thing, we can just enter encoding JSON. And the same thing. First thing we do is t old. Great. Oh, yeah, I forgot. By default, the benchmark now also gives you allocation information, which is useful. So the change that I want to do is, if we look at the decode file, so this is the code that I ended up committing to master. It's pretty much the same thing I did live, but with comments, because comments are useful. Now, my theory is that using this map is good, but it's not great, because maps are actually pretty expensive. So maps are great if you've got thousands and thousands of elements, but realistically, when you're decoding a struct, the struct is going to have less than a dozen fields, right? So hashing the string and then looking through the map, comparatively, it's quite expensive compared to instead of just iterating over the list. But what was expensive from the previous implementation was the equal fold call. So here's what we're going to do. We're going to say if the length of fields.list is small, and I'm gonna guess, and I'm gonna guess that 20 is small. And nobody please look that up. So if the length is small, then we're gonna do pretty much the same thing that this does. But we're gonna do if bytes.equal ff name bytes key. Cool. Cool. And otherwise, if it's large, then we're going to use the map. And only in the case where we still haven't found a match, then we're going to do the expensive case-insensitive linear search. Great. That looks like it. Let's see what test broke this time. Oh, great. Go imports. Oh, nothing broke. That's useful. Great. So t new. So who thinks this is going to be useful? Please raise your hands. I see very little confidence in my abilities. Okay, let's see. 1.5%, that's not bad. I would say that should go into master. So, well, sorry. I should say, I would say I can mail this and then somebody can review it. Somebody in the audience, maybe. So what we can do, we've got time left, and the internet maybe works. So what we can do is, new branch, JSON, oh my god, so fast. Encoding JSON, decode struct, faster struct decoding when there are, okay. Again, this is realistic. I want to write something short. Encoding JSON. Decode small structs faster. I think that's okay. I'm doing this live at GopherCon. Please go easy on me. Maps are non-trivially expensive if, well, no. If we have few struct fields, a linear search is faster and simpler than using a map. do that. And I forgot to copy the bench stat. So we want to copy all of this. By the way, what I'm doing now is showing you how I'm actually going to send that as a patch to go. So I want to indent that. Great. To do for myself, add a benchmark that shows the perf. So I guessed that 20 is a good number, but maybe 20 is too low or too high. So in the future Daniel will write a benchmark that basically benchmarks the speed of the old and new code for example, 1 field, 10 fields, 100 fields, 1,000 fields. And with that, maybe I can find a better number to separate the two approaches. Great. So with that, we can do git code review mail. And if the demo gods are being merciful, success. Great. Let's go look at it. Great. So who in the audience can review this? I think we've got time. Oh, Caleb is doing it. No? Oh, no, he's not. Cool, great. That's pretty much it. So as you can see, so I was trying to show two things. First is how in real life somebody would do little optimizations in Go, and the other side of it is sending patches for those is not difficult, at least updates. Oh, there's a race for it. Amazing. So do I get trybots 3 times now? Great. So hopefully this is going to be helpful for you to benchmark and optimize your own code. But if you want to join me in benchmarking and optimizing the standard library, I can help, and I'll be happy to get more hands. Thank you.